Hello, today we're doing 4.2 Riemann sums. Go ahead and try the warm-up. This is an optimization problem, so you're finding the maximum area of a rectangle if its perimeter must be 42. Okay, so I'm going to just sketch my rectangle here. I'm going to say that it has a width of x and a length of y. I don't know either of those things, so those are my variables. I do know that the perimeter is 42. So 2x plus 2y is going to equal 42. And I'm trying to maximize my area, xy. Okay, so I want to go ahead and solve for either x or y. I'll do solve for y. And I want to plug that into my area formula. Distribute, and go ahead and take my derivative. Set equal to 0. So x is 10.5. When I plug that in to x, I will find that y also equals 10.5. And so my maximum area, is going to be 10.5 squared, which is 110.25 square units. All right, today we are learning about Riemann sums. This is a little bit abstract. There's a lot of letters and not a lot of concrete numbers because everything is sort of theoretical. So I really want you to pay close attention. It does make sense if you really focus and think about it, but you can't just kind of half pay attention today. All right, so Riemann sums were invented by German mathematician Bernhard Riemann, who lived from 1826 to 1866. They underlie the theory of definite integrals studied in the next section. Imagine that we have some function f of x defined on a closed interval a to b. So I drew a little picture. This could be any graph. We're just going to look at this specific graph today. Like the function in the figure, f may have negative as well as positive values, meaning sometimes it might go below the x-axis or above. We subdivide the interval AB into subintervals, not necessarily of equal widths or lengths. To do so, we choose n-1 points, x1 through xn-1, between A and B. And the only reason there's one less than n is like if I was going to cut this box into 5 sections, I would draw 1, 2, 3, 4 lines to do that, right? All right, the first of these subintervals is x0, x1. And the kth subinterval is xk minus 1, xk. The width of the first subinterval is the change in x sub 1, which is equal to x sub 1 minus x0. And the width of the kth subinterval is the change in x sub k, which is x sub k minus x sub k minus 1. So basically we're just minusing, let's say one of our things starts at 3 and ends at 3.5, then the width of that would be 0.5 because you just subtract those two. That's all that's saying. And since we don't know the numbers, we're just saying everything as k, just to keep it general. All right, each subinterval, we select some point. The chosen point in the kth subinterval is called c sub k. The point c sub k, f of c sub k, is where the top of the rectangle is. Okay, so just look at the picture. It'll help make it make sense. We have each rectangle that we've drawn here. In each rectangle, we're picking a point. That point is where we basically just say, okay, this is where I'm going to the top of the rectangle. I go up until I hit F, until I hit the graph. That becomes the height of the rectangle. Okay, that's all it's saying. So the width of the rectangle is subtracting those two numbers. The height of the rectangle is in between those. I pick a point, I go up to the graph, and that's where I make my height of my rectangle. Okay. All right. So like for instance, here, this was obviously the C right there, because that's where they made the height. Each rectangle's area is f of c sub k times the change in x sub k. Okay, so that should make perfect sense to you, because the f is how high it goes up, meaning the height of the rectangle, and the change in x sub k is just the difference between those 2 points, so the width. The sum of all these products is the summation from k equals 1 to n of f of c sub k times the change in x sub k. So basically, it's just saying, hey, find the area of every single one of these rectangles and add them up. It is called the Riemann sum for f on the interval a to b. There are many such sums depending on the number of subintervals n that are formed. Okay, so all of this, the point of all of this is we are trying to find an estimation for the area under this curve. We're trying to figure this out, okay? And so what we're doing is we're cutting rectangles, and we're kind of hoping that like, hey, right here, it kind of went over the line. But right here, it went under the line. Those are going to balance each other out, okay? And there's a lot of different ways to do this, because I can make a lot of rectangles. I could make a few rectangles. I could make them really wide or really narrow. I could choose my C right there, or maybe I could have chosen it there and my rectangle would have been a little bit higher, okay? If each subinterval has an equal width, then the change in x is b minus a divided by n. Okay, so now we're saying instead of having all these random rectangles with random widths, let's make them the same. So if I'm going from A to B, I want n rectangles. I'm just going to take that difference, cut it into n equal pieces, and I'm going to make all my rectangles exactly the same. If we choose the point c sub k to be the right-hand endpoint of each subinterval when forming the Riemann sum, then we have the Riemann sum formula. So this is a formula if we are going to choose the right-hand part of each rectangle to be the c. Okay, so what that means is on each one of these rectangles, I would pick the right-hand side of the rectangle. That's going to be the top of the rectangle each time. Okay? And here we have our formula. So this is basically finding the height of that rectangle that you want, the kth rectangle. And then remember, all of our widths are the same. So that's always going to stay the same, b minus a divided by n. And that's just the formula for this. Similar formulas can be obtained if instead we choose c sub k to be the left-hand endpoint or the midpoint of each subinterval. In the cases in which the subintervals all have equal width, change in x, b minus a over n, we can make them thinner by simply increasing their number n. So if we pick less rectangles, our rectangles are wider. If we pick more rectangles, they're skinnier. And the more rectangles you use, the more accurate your answer. All right, 2 formulas. I just stuck them in here. We have a formula for k squared and a formula for k cubed. So remember yesterday, we had the formula for k, and I put a big yellow star by it, and I said, if you remember this formula, you are going to thank yourself so many times because it saves you so much time. Well, here's 2 more formulas. Again, very, very, very handy. You don't have to sit there and add up a bunch of numbers. You have a formula to get the answer right away. So maybe put a big star by these fun facts. Try to remember that these exist so that you can look back in your notes when you come across them and use the formulas. Save yourself oodles of time. All right, we're going to try number 1. We're going to graph the functions over the interval. We're going to partition them into 4 subintervals of equal length. And then we are going to add to our sketch rectangles that are the Riemann sums. And we're going to make 3 drawings. We're going to do the left-hand endpoint, the right-hand endpoint, and the midpoint of the kth interval for each rectangle. All right, here we go. So let's look at A. X squared minus 1. All right, let's go ahead and sketch the graph of x squared minus 1. We're going from 0 to 2. Okay, so I have 0, 1, 2. This is x squared minus 1. So it's basically your normal parabola, but we're going to shift it down 1. Okay, so instead of 0, 0, we're at 0, negative 1. Instead of 1, 1, we're at 1, 0. And instead of 2, 4, we're at 2, 3. All right, there's my thing. They wanted us to cut this into 4 equal rectangles. So my first rectangle would be there, and then here, and then here, and then there. Okay, there's 1, 2, 3, 4. All right, now remember we're doing 3 of these. The first one is going to be our left-hand end point. Okay, so what that means is each of my rectangles is the height of wherever the left side of the rectangle hits the graph. So here's my first interval. On the left, I have to go all the way to there to hit the graph. So there's my first rectangle. Okay, see how I went all the way to the graph. Next interval, I'm going to draw it in a different color so I can help you out here. Here's my next interval. I start on the left, I go up to the graph, stop. There's my rectangle. Okay, next one. I'm going to go back to red. This one's a little bit strange because here's my width of my thing, but guess what? My left-hand endpoint is on the graph. So there's no rectangle there. The height is 0. Okay, because I'm already touching the graph. All right, and then the last one, here it is. Start at the left, go up to the graph, and make my rectangle. All right, next we're going to do the same thing. This was my left-hand endpoint. Next we're going to do right-hand endpoint. All right. So sketch your graph. And this time we are still having 4 rectangles, so cut that into 4 sections. But this time we're going to use the right-hand part of our rectangle. Okay, so here's my first rectangle. I want to go to the right hand part. I'm going to go down to the graph, scoot over, make my first rectangle. Okay, next one. This one, I drew my graph a little bit wrong. So it's supposed to hit right there. So this is actually one where my right hand endpoint is on the graph. So there's no height there. Okay, next one is here. Go up, make my rectangle. And then the last one is here. Go up, make my rectangle. So this is the right hand endpoint. All right, we're going to try the center, midpoint. Midpoint. Okay, 1, 1, 2, 3. Draw my parabola. Okay. All right, it's got my 4 equal width rectangles. So here's my first rectangle. And on this one, I'm actually going to the midpoints to make my height. So I'm going to go there, and there's my first rectangle. Okay, next one, midpoint, go up to the graph. That's the height of my second one. Third one, midpoint, go up to the graph. That's the height of my third. And fourth one, here's the midpoint, go up to the graph. That's the height of my fourth. All right. Now notice each one of these, I would get very different areas for each one. So we kind of have to decide the best one at times, which one looks the most accurate. All right, let's go to the next one. This is a sine graph from negative pi to pi. Okay, so let me graph it. Negative pi to pi. Sine starts at 0, hits 0 at pi, hits 0 at negative pi. It goes up to 1 at pi over 2. It goes down to negative 1 at negative pi over 2. And those are actually going to be where my rectangles are formed because I need 4 rectangles. All right, this is my left hand. So my first rectangle right here, the left-hand side of it is actually on the graph, so there's no rectangle formed. Next one, left hand is right here, goes there. Okay, next one, left hand's right here, it's on the graph, no rectangle. Next one here. Okay. All right, let's sketch the same graph. Oops. So same graph I did, 0, 0, 0, up to 1, down to negative 1. Okay. I can hear Erin like, how do you write so fast? Oh my gosh, I'm still on number 1. All right, so on this one, we're doing our right hand endpoint. So my first rectangle, the right hand is here. I go down to my graph, make my rectangle. Next one right here, my right hand is actually on the graph, so no rectangle formed. Next one here, up there. And then this one here. There we go. All right, last one we're gonna do is center the midpoint. Okay, so sketch your midpoint. Sketch your sine graph. Okay, here's my 2 extra points to make it 4 rectangles. All right, so on this one, I'm actually using the center of my rectangle to go down to my graph. Wherever it hits is where I'm forming, that wasn't great, is where I'm forming my rectangle. Okay. Okay, so you are doing some of these on your homework, just sketching a graph and then using left hand, right hand, and midpoint to make rectangles. So make sure you understand what's going on those. Hopefully it makes sense. All right, so on example 2, we're actually going to use the Riemann sum formula that we just talked about on the previous page, and we are going to evaluate these as n goes to infinity. And so the point of this is, remember we said n is how many rectangles we're making. If we only make a couple rectangles, our answer is not very accurate for the area under the curve. If we make more rectangles, it gets more and more accurate. So on these ones, we're actually going to let n go to infinity. And what this does is it actually gives us the correct area under the curve, which is kind of a big deal. If you think about it, this guy Riemann figured out a way to find the area under these crazy curves, right? And that's not easy because curves are not easy to find the area of. So he developed this formula, and if we let n go to infinity, meaning an infinite number of rectangles, we're going to get the precise area under these curves. All right, so let's try number 2a. So our function on this one is f of x equals 1 minus x squared over the interval 0 to 1. Okay, so the first thing we're going to do is write down our formula. So we have the limit as n goes to infinity. And we are actually using our formula from the previous page. Okay, so k equals 1 to n. And the formula is f of a plus k times b minus a over n. So I'm using this formula right here, guys. Times b minus a over n. So your b and your a are these right here. Okay, so my A on this one is 0, and my B is 1. Okay, so now we're going to plug into the formula. So first thing I want to do is I want to figure out my A plus K times B minus A over N. So I have 1 minus A, A is 0, plus K is K, times B minus A, that's 1 over N. This is all squared. Where am I getting that? From the formula right here. So here's my 1 minus X is that stuff squared, times B minus A, which is 1 over N. Okay, so just really, really quickly, I just want to point out this right here, that is this, okay? I'm plugging it in to X in this equation. So notice this whole thing is 1 minus X squared, where I'm plugging this in for X, which is what they told me to do over here. You can't even see it anymore because I've circled it so many times, but see how it says F of that stuff? That's what I'm plugging in for the X. So that's how I get that. All right, I'm going to take a moment to simplify this a teeny tad. Okay, so here we go. We have limit as n goes to infinity, Riemann sum from 1 to n. So here I have 0 plus k over n squared. Well, the 0 does nothing. So this is really 1 minus k squared over n squared times 1 over n. All right, let's distribute the 1 over n. Limit as n goes to infinity, Riemann sum of k equals 1 to n, 1 over n minus k squared over n cubed. Okay, I brought in the 1 over n. Okay, at this point, I want to use my Riemann sum rules that we talked about yesterday to make this a little bit different, something I can attack a little bit easier, okay? So the first thing I'm going to do is I'm actually going to pull out, or no, I'm going to separate with my minus, but I'm also going to pull out any constants that I have. So remember, on this, n is my upper bound here. It's where I'm ending. So n is a constant. I'm going to pull that out. Okay, so let's look at this here. So we have limit as n goes to infinity. On the first one, I pull out the 1 over n, because remember what I said, that's a constant. Even though it looks like a variable, we don't know what it is. It is a constant because k is my variable when I'm doing Riemann sums. All right, when I pull out the 1 over n, there's just 1 left here. Minus, and then here I'm going to pull out the 1 over n cubed. Sorry, my summation symbol looks pretty bad. I'm trying to squeeze everything in here. And there's k squared. All right. What I'm going to do now is I'm going to go ahead and do my first part right here, which is my Riemann sum. And remember, this is a formula from yesterday. When you have a constant here, you just do 1 times n, and that's your answer, right? Okay, so this gives me limit as n goes to infinity, 1 over n times n. So that's just going to be 1 minus. Okay, for the second part, keep your 1 over n cubed out in front. This part right here, if you recall at the middle of the lesson today, beginning, middle of the lesson, I made you guys put a star and circle those fun facts. This is one of those fun facts. We have a formula for this right here. Okay, so we're going to plug in that formula. So this would be n times n plus 1 times n, 2n plus 1, all over 6. All right, we're doing good. Okay, so remember on this first one, the n's are going to cancel. So limit as n goes to infinity of 1 minus. Okay, here I actually want to take the time to work this out. Okay, so on my numerator, I want to distribute everything out. And I'm going to do that for us right now. I'm not going to work that out in detail. But if you were to distribute everything out, you get 2n cubed plus 3n squared plus 1. And then on the bottom, I have the 6 and the n cubed. Okay. Well, we're almost done now because we know how to do the limit as n goes to infinity. So what we're going to do is we're going to divide everything by n cubed, right? So this gets divided by n cubed, this gets divided by n cubed, this gets divided by n cubed, this gets divided by n cubed. And so what ends up happening is I get 1 minus everything that still has an n on the bottom. As n goes to infinity, it goes to 0. So here I just get 2 over 6, or 1/3. So the answer here is 2/3. So the area underneath the curve 1 minus x squared from 0 to 1 is 2/3. Okay, we're going to try B. I'm going to start it up above where A starts because I just know I'm going to need all of the room. All right, so let's look at B. We're going to try this all over again, give you guys another shot at kind of understanding this and seeing how we do it. So on B, we have 2x cubed over the interval 0 to 1. So my A, again, is going to be 0, and my B is going to be 1. All right, so we start by doing the limit as n goes to infinity of the summation from k equals 1 to n. And then now we're doing our formula. So let's revisit our formula from the other page. So the formula we're talking about is right here. Okay, so the first thing we want to do is find this part right here in red, a plus k times b minus a over n. So on this one, a is 0 plus k times b minus a is 1 over n. Okay, so in this one, we still have k over n for what we're plugging in there. And then this one is 2x cubed, so we're plugging that in 2k over n cubed. All right, plug that in, times b minus a over n. So b minus a over n, b minus a is 1, so 1 over n. All right, we do want to take one step to simplify this a little bit for ourselves. So this would be k equals 1 to n. We're going to have, you know what? I'm going to bring the 2 out because it doesn't need to be in there. So this gives me k cubed over n squared. Actually, I can bring the n squared out as well. I'm going to do that in another step so that you can see it. All right, so there's my, you know what? I'll take the 2 out in the next step too. So 2k cubed over, and it's actually n to the 4th, not n squared. I'm sorry, because from the first one here, sorry about that, I have n cubed, and then I have another n right there. So this is actually n to the 4th, sorry. All right, here we go. Taking out the constant. So remember, k is the only variable. Even though n, I know it's a variable, but we could pick any number for n, it would be a constant. So we're going to take out the k, or sorry, we're only going to leave in the k. So we have 2 over n to the 4th, Riemann sum from k equals 1 to n, k cubed. All right. Now, most of you are probably thinking, hey, that was the other fun fact that Mrs. Hannon gave us, which is that we have a formula for k cubed. Woohoo! All right, so we're going to use that. So that is going to be limit as n approaches infinity, 2 over n to the 4th times, and my k cubed formula, which is n squared times n plus 1 squared over 4. notice I just brought the squared in. Okay, I squared the top, I squared the bottom, became a 4. All right. Okay, so let's try to reduce some stuff before we go ahead and do our limit as n goes to infinity. Okay, well, I see 2 of these can cancel. This can cancel. Okay, let's distribute out the top. So limit as n approaches infinity, n squared plus 2n plus 1 over 2n squared. Okay, so we're going to infinity, so we're going to divide everything by the highest power in the denominator, which is n squared. Anything that has an n on the bottom is going to go to 0. The things that have n squared are going to cancel, and I'm going to get 1/2. And that is the area under the curve 2x cubed from 0 to 1. All right, so homework is going to be trying some similar to what we did in the notes. So like on number 1, A and B, you're drawing the 3 graphs, drawing your rectangles. For number 2, you are trying what we just did on example 2 in the notes, okay? Do your best. Don't forget about your rules, meaning you can pull out constants, and you have those 3 rules. So you have rules for k, you have rule for k squared, and you have a rule for k cubed. So do not forget those. You have 3 things that make it so much easier to do those summations, and you kind of need them in order to do the problems where the n is going to infinity. All right, good luck.